In the last video, which I recommend you watch first, I looked at this special case for differential equations, linear second-order differential equations, where the characteristic equation has two complex roots. And in this video, I'm going to look at the same class, but for recurrence relations, so second-order linear constant coefficient recurrence relations that have two complex roots as their for their characteristic equation. So I'm going to kind of go quickly over the details here. If you want more in-depth details, watch the last video. So Euler's formula, basically what it gives us is a way to convert back and forth between polar coordinates for complex numbers involving only r and theta, and Cartesian coordinates involving a real part and an imaginary part. So in all of the derivations I've done for the solution to second-order linear constant coefficient recurrence relations, a special case has come up, like a decision point in the derivation of the solution, where you have to either consider the two roots to the characteristic equation as being the same or different. And so really, the repeated root case is the special one. The complex root case is a lot less special. While when you're deriving the solution to these things, there's no point where you have to decide, are the roots real or are they complex? So just as usual, if we have a recurrence relation like a fn plus 2 plus b fn plus 1 plus c fn is equal to 0, with roots lambda 1 and lambda 2, even if they're complex, the solution is still going to look like this. So now what I want to do is go through a similar process in the last video to figure out a better looking version of the solution here. So we're considering this case here where lambda is equal to alpha plus or minus I beta. So the first thing I can do here is I can replace these two values for lambda. So the first one is alpha, I'll say plus I beta, and the second one is alpha minus I beta. Okay, the first thing I want to do here is convert to polar coordinates. So I'm going to do that by using this formula here. Alpha plus I beta is equal to r e to the I theta. So here what I have is r e to the I theta, and this is all to the power of n. Over here it's a little bit different. Here I have a minus sign, so well, what if you replaced theta with negative theta? Then cosine of negative theta, that's just cosine of theta, that would be unchanged. But this sign, the sign of this term here, would be negated. So this would be minus IR sine theta. That is, if you replace theta with negative theta. And so what you'd have is an alpha minus I beta. So all I have to do for this other one here is I just replace this with r e to the negative I theta. And this is to the power of n. Okay, and so now what I can do, similar to the process with the differential equations, I have this exponential function I can factor out, r to the n. That's a common factor here, so I'll take that out. And then I'm just going to use an exponent rule here to write this as e to the I n theta. And then over here I have e to the I negative n theta. Okay. And so from here I'm just going to simply apply Euler's formula, which is this one here. E to the I theta is cosine theta plus I sine theta. I just have a slightly modified argument. Instead of theta now, in this one here I'm dealing with n theta. So here I'm going to have c1 times cosine n theta plus I sine n theta. And then over here, instead of theta, I have negative n theta, and I can just keep using that same trick. Well, if I put negative n theta in for cosine, it's just still a regular cosine. I can just get rid of that negative sign, and then the sine one gets swapped. Okay, and so you can kind of see the same type of thing is unraveling here. All I have to do is group these cosines together and group the sines together. And then from here, I can just redefine those arbitrary constants. Call this one K1, call this one K2. So this is r to the n, K1 cosine n theta plus K2 sine n theta. So let's compare with the solution to the differential equation. So this is Fn, the solution to the recurrence relation. The differential equation of the same type with the same characteristic equation had this solution. So we still have an exponential function that controls the amplitude here, and we still have linear combinations of sines and cosines. Keep in mind with the recurrence relation here, kind of oddly, n is the variable, r and theta, those are just constants, they're just parameters. But the real interesting thing here is that with the differential equation, alpha and beta, those are the two parameters that are playing the big roles here. And alpha and beta, those were the Cartesian coordinates of the root of the characteristic equation. Whereas with the recurrence relation, the two constants that show up in the solution are the radius and the angle of that point, the polar coordinates. And so they are kind of more or less playing the same roles here. The radius is just affecting the growth, the exponential growth or decay in amplitude. Let me draw a little picture here. So if I call this n, and then this axis would be like f of n. So you have like these exponential limits, like top and bottom. But this is a discrete function, so you have kind of like this type of thing. Here they're much closer together. I mean, they're the same width from left to right, but the points themselves might be slightly different positions. Anyway, so what you can see is that the radius is controlling the growth of the amplitude of this discrete kind of wave thing. And the angle, this is, remember, n is the independent variable here. Theta is a constant. So theta is telling you the frequency. So this is kind of weird. The radius here, it looks like with this type of exponential function, if r is less than 1, like if r is between 0 and 1, then that's when you're going to get an exponential decay. And if r is greater than 1, then that's when you have an exponential growth. So there's some point here, radius 1, where you have constant, if you have this radius, you'd have like constant amplitude. And then as radius increases, if we like drag this point out this direction, then this would be increasing, or like exponential growth of amplitude. And then moving towards the origin, this would be like making it have an exponential decay in amplitude. Then the angle depending on where we have this angle, that's going to change the frequency. And notice that like you have something special going on here if theta is a multiple of pi, because n is always just going to be an integer. So if you want this thing to actually repeat, then theta has to be like a multiple of pi. Anyway, I just find that pretty interesting that with the recurrence relation, the two important quantities are radius and the angle, the polar coordinates of the roots of the characteristic equation, whereas with differential equations, they're the Cartesian components that are important. This also gives you kind of like a method to solve these recurrence relations that have complex roots. All you have to do is find the distance from that complex point in the complex plane to the origin, and then you just have to find the angle of it, and then you're pretty much done. Again, oftentimes theta might be like a multiple of pi, and so you might be able to simplify these sine and cosine expressions to get something that is just like more simplified.